Hello everyone, it's high time to start our webinar about AI-powered scheduler for Kubernetes. My name is Paweł Parol.
And my name is Tomasz Janaszka.
And today we're gonna talk about the POC we have developed here at CodeLine for intelligent scheduling of workloads in Kubernetes. Tomek, I think it would be good to start with a kind of brief explanation of what the scheduling Kubernetes is.
Yeah, because it would be much easier to understand the concept, which is the second point in our agenda. Also, next we will explain the POC architecture and POC results.
And of course, we plan to have a demo.
Yeah, we hope that it will be convincing.
And finally, we provide you with some remarks and conclusions about the topic. And of course, we plan to have a Q&A session as usual. So please remember, you can write down your questions in the YouTube chat window, and we'll try to answer them at the end of this session. Okay, so here we go.
Yeah.
So what the scheduling of workloads in Kubernetes is. So imagine there's a situation that there's a request coming to the Kube API server to run a completely new pod. As you may know, the pod is the simplest Kubernetes workload object representing a kind of application, job, or process inside. And in short, the idea here is just to find an appropriate node in the cluster on which such a pod can be deployed on. As simple as that. Unfortunately, it is much more complicated underneath. This is the diagram showing the Kubernetes scheduling process. And as I said, it's quite complex, multi-stage process, in fact. But to give you a slightly better sense of what's going on, we can point out four main phases here. So in the first one, the pods waiting to be launched in the cluster are queued. And normally those who arrive first will be served first. This is the general rule, unless you configure it differently because you still have such an option. Next, you've got a filtering phase when you eliminate such nodes as potential candidates for placing a given pod on them. And there are many different criteria that can apply here, like Tencent tolerations, like anti-affinity rules, and other features that Kubernetes offer to you. But we'll not go into detail today. And after that, you've got the scoring phase. And here, all remaining nodes receive scores, which are some numbers, actually. And once again, many different criteria can be used to score the nodes. For instance, a node with more free compute resources can get a higher score than others. But it's not only the case. Nevertheless, one node will finally get the highest score. And since then, the process of launching the given pod on the node will begin. And this happens during the binding phase. So this is how it all works. Okay, so since we all understand what the scheduling Kubernetes is, at least to some extent, I believe, I think now we can try to explain the idea we applied for the so-called optimized scheduling.
Thank you very much for this introduction. When we would like to now we would like to explain the concept. But before we dive into details, I would like to say a few words about the resources, how they are managed in the Kubernetes environment. So it is highly advisable to provide requests and limits for each running container or the containers that need to be scheduled. And the request expresses the minimum amount of resources that are needed for the efficient operation of the container, of the processes in the container. And limits defined are higher and are usually set for accommodating the sudden spikes in the resource consumption. But the container cannot reach more than the limits. If it tries to do it, it can be evicted from the cluster or can be slowed down. But from the point of view of scheduling, the requests are important because the Kubernetes is aggregating the request of the containers running in the each cluster node and based on that is able to indicate the next worker nodes for the consecutive scheduling actions. But it is not easy way to provide appropriate requests and limits. Consider the situation in the slide when we have the say application that is consuming the resources in the cyclic way. So we can observe the huge disparity between the resources consumed in the peak and in the off-peak periods. There are many options how to set the request, but you can notice the highly recommended requests are to set them close to the maximum and the limits higher. And in that way, we are providing the right level of the resources for our application, but the overall utilization of the cluster can be low because of the existence of the off-peak periods. Alternatively, we could provide requests closer to the average usage of the resources and limits above the observed maxima. In that way, we are allowing Kubernetes to schedule more pods, but this is the risk related to overcommitment. So it may happen that temporarily many pods will consume too much resources exceeding the total capacity on node, causing various effects of instability like restarts, out-of-memory errors, and slowing down the processes. So we are in the delicate task of striking a balance between the setting, assuring appropriate level of the resources for the containers and between the efficient utilization of the across the cluster nodes. Therefore, we see a potential for applying data science and machine learning methods to better understand the characteristics in time of our workloads, and such knowledge could be used in the scheduling process.
Mm-hmm. And do you think we could elaborate a little bit more about what exactly we can learn from such an analysis of resource utilization data?
Yeah, for instance, we could quite easily detect if our workload exhibit the cyclic behavior in time. And based on that, we can evaluate its pattern of the resource consumption. And that is, it aids to forecast the resources that will be computed by particular workloads. This is the one point. Of course, not all the workloads are exhibiting such a cyclic behavior. In that case, we can use standard machine learning methods for forecasting what will be next based on the traditional time series forecasting. Also, we can focus on the distribution of the statistical features of such a time series, for instance, using maxima and higher level percentiles. So here we cannot evaluate the pattern, but can we provide some forecast? Also, if we consider the batch processing and jobs and cron jobs instantiate a set of concurrent pods. Usually the pods are doing the same code, executing the same code on different data, and very often they are exposing the similar behavior in terms of the resource consumption. So based on the historical runs on such a pods, we can also evaluate the patterns of the particular pods belonging to particular jobs. And such information also could be used in the scheduling process.
Mm-hmm. And I think it will be very useful also to explain how to make use of all this information. What do you think?
Yeah, I will give you two examples. One we call the compensating characteristics. Consider that you have two applications that exhibit the cyclic behavior, like here. This is very frequent pattern for the business application and say customer applications. So such applications are loaded more during the working hours and less in the evenings. For the customer, the application, the behavior is opposite. So we can say when one application is consuming high amount of resources. Another is consuming low or moderate amount of resources. So having those knowledge about that workloads, scheduler can intelligently schedule them on one node instead of two. And because the cumulative resource consumption of those two applications is not surpassing the total capacity of the node.
Mm-hmm. Yeah, yes, but this is for application-related workloads, let's say. But you've also mentioned the job spots.
Yeah.
So maybe you could explain also how to use the learn patterns also for them.
Yeah. So if we assume that we could elaborate what will be the consumption in the forecasting horizon, and if we have a new task to schedule a new job, then if we know, of course, if we learn the pattern for it, we could just conduct the comparison of the characteristic and easily see if accepting this both we are surpassing the total capacity. In this situation, we will say no, we cannot accept. But a little bit later here, knowing the cyclic behavior of the application and knowing that this is the off period, we can accept even two such a pods, increasing the overall usage utilization of the resources.
Mm-hmm. Okay, so to sum up, what the intelligent scheduling could be, according to the approach that we propose. So first, we want to learn the resource consumption patterns for workloads. So this is the first step. Then we would like to forecast the future utilization for worker nodes. And finally, select the best worker node for a new workload coming to the cluster.
Yeah, exactly what is scheduling doing, but based on the learned characteristics in time.
And now the question may arise, why to do that? So I think, first of all, we would like to have a more efficient use of existing resources, meaning that the total size of the cluster is likely to be smaller. Secondly, would like also to reduce the total number of errors, restores, eviction of workloads. And also, it would be very important if we make a cluster administration a little bit easier, meaning that the cluster admins would have to perform less analysis, as the intelligent scheduler would do most of the work in an automatic manner. And if you wanted to describe the idea of intelligent scheduling in just one sentence, we could say that the standard Kubernetes scheduler takes into account only some declarations regarding the use of resources, which later on may turn out to be inaccurate somehow. I think it's always a risk. On the other hand, our intelligent scheduler learns the characteristics of real resource consumption. And this is the main difference. Okay, so that was the idea. I hope it was clear. Now let's take a look at how implemented is as a proof of concept. So we told you that we wanted to learn resource utilization characteristics for workloads, but first of all, we need to collect the relevant metrics somehow. And for that purpose, we use the well-known Prometheus. Next, we have an analytical model that we developed, and its role is to first take the metrics from Prometheus. This is the first step. Then identify resource utilization patterns for existing workloads, and then forecast future resource utilization characteristics for those workloads. So this is how it works. It is important to note here that currently our POC takes into account only memory-related metrics, but of course the target solution would use also CPU-related metrics or other types of metrics if needed. But getting back to our story, the forecasts are stored in the InfluxDB, which is a popular solution for time series data. And now another analytical models comes to play, which role is also to provide forecasts, but this time for the cluster nodes. Yeah. And in order to do that, it takes the following steps. First of all, it asks the Kubernetes API for a list of workloads running on each node. Then it takes the individual forecast from InfluxDB And finally, it provides a kind of aggregated forecast for each node in the cluster, and it's stored in the database as well. And finally, another component comes to play, which is called a node evaluator. And it takes the forecast from the aggregated forecast from the InfluxDB. And based on that, it calculates scores for each node. And this is an ongoing process.
Yeah, so these components are clear, I hope so, also for our guests, but I think it's time to show how we integrated it with the Kubernetes scheduling framework.
Yes, this is a very good point. To understand that, first we need to go back to the picture I have already presented to you at the beginning of our session. So what is important is that every single stage in this pipeline offers a kind of extension point where you can add some business logic. And such a logic is represented by a set of standard plugins, which are responsible for some different aspects of scheduling Kubernetes. And the good news are that you can also add your custom plugin, since this is an open framework. And this is exactly what we did. We have developed our own plugin, which communicates with our analytical components described in our overall picture. And in fact, this completes the picture. A couple of words about the technology stack that we use to build our POC. So the platform is, of course, Kubernetes. For observability functions, we use Prometheus, Grafana, and Grafana Loki, which is quite a useful tool for collecting logs from the cluster. The database is InfluxDB, as we have already mentioned. All the analytical modules have been written in Python, but we also use a plenty of different tools and libraries to provide AI functions for them. And lastly, the custom plugin for scheduling has been developed in Golang, as this is the main language for Kubernetes. So I think now we are in a very good place to start talking about the results of our POC.
Yeah, we would like to demonstrate one use case we selected. We called it efficient job execution. I think my introduction to the concept also will help to understand this use case. And we are using our cluster lab that consists of 4 worker nodes, each having 16 gigabytes of memory. And we modeled 4 deployments for 4 cyclic applications that are consuming the memory, ranging from 2 gigabytes to 10 gigabytes, 1 replica, and the applications have different memory consumption characteristics, as we could see in our next slide. So this is the initial situation of the running application on 4 worker nodes. And we would like to use their memory in an efficient way, executing 3 jobs that are different. They are instantiating the concurrent pods. To complete each job, we require to have 50 completion of particular pods, and they are consuming the memory up to the 4 gigabytes. And we would like to complete the job as fast as possible, putting the concurrency to the highest level as high as possible. And we would like to have all deployments concerning the applications and the started job uninterrupted, which means, so we would like to schedule the job pods in a way that are not causing the out-of-memory errors and restarts. This is our assumption. And we modeled the characteristics of the job pods in this way for these 3 jobs. I hope that the names are self-explanatory. Flat job is consuming the similar amount of memory during the execution time. High start job, it means that it is consumed more at the beginning from start, and low start is consuming less at the beginning but more at the end.
Yes, I think it is clear.
Okay, so just to outline a few things, normally we will use the request above the peak for our applications, and in that way, a standard scheduler will be able to schedule only single job pod per each node in that time. We would like to show that our scheduler is able to decide in a more intelligent way based on the learned characteristics and to place the pod in the off-peak periods. This is the assumption for this use case.
Mm-hmm. I think that looks very good, but maybe to get a slightly better feeling of it, we could show how it works in practice. What do you think?
Okay, let's check everything is working. I will show a couple of dashboards that are communicating with the working setup. So in some places, I will switch off the refreshment just to have the, say, stable view and to better extent. Yeah. So let's switch to the first dashboard here. It is the dashboard presenting the how our analytical components recognize that our applications are cyclic. And here, it draws one cycle and put it in time. So in that way, these are the different characteristics recognized for our applications. In this dashboard, we can easily check if how the peak and off-peak periods are relates to each other in terms of the time. And the next dashboard is for the recognition of the particular job pods, how they are consuming the resources, and the shapes are similar as we assumed in our use case. And this is the extract of the historical usage of individual pods belonging to particular jobs. So we have a common pattern for the jobs belonging to flat job, high start job, and low start job. Next, I will switch to the logs, showing the communication between the scheduler. I will zoom in and switch off just to have some good points here to explain what is going here. This is the exchange of the messages between the scheduler and node evaluator. And scheduler is asking if a new job pod belonging, in this case, to low start job, can be executed on particular workers. And our node evaluator is responding true and false. True means that the pod can be accepted at the given moment, based, of course, on the characteristics. In case we have here 3 worker nodes at our disposal, the node evaluator also is computing the scores. So in that way, based on that, the scheduler is selecting the best worker nodes and forces our components to update the forecast on the worker nodes. Now I will switch to the 4 consoles. This is the watch command that is presenting using the kubectl the job pods that are in the pending state, so they are waiting for the time based on those characteristics, what are being executed currently, and what is completed. There is also one console that is presenting the job pods that are killed due to the out-of-memory error. It is empty. It means that our components are working properly are evaluating the patterns and forecast, and our scheduler is working as we expected. And now I will show the last dashboard. I think the most complex ones. So it is presenting the memory consumption of particular pods and also the application and job pods. In different colors denotes the different pods. And I would like to show you some key points. What we could see here. We could see that our scheduler is instantiating more pods, say during the valley, during the off-peak periods. In that way, effectively using the available resources. And less pods in the peak periods of our application. This is the consumption of our application. And here for particular job pods. And this is the stacked version of the presenting the cumulative resource consumption. And here also we could notice that we have the gap here. So this is the a kind of safety margin. We set it to the 10%. So deciding if accept or not accept the new pod, we are just trying to keep this margin here in order to not to cross the border, even if our forecast could not be as accurate as we could expect. So this is the the last dashboard. And backing to our presentation, we have a table, but this time for 10 pods for the completion of particular jobs. When we use our scheduler for the completion of those jobs, we require 16 minutes, and using the standard scheduler, 37 minutes. So
in that particular case.
In that particular case, 2.5 faster.
Okay, so I think it's time for conclusions now.
Please.
So today we presented a POC for intelligent scheduling of workloads in Kubernetes, which makes use of resource utilization characteristics. So we have discussed the solution architecture. We have also shown how we integrated our analytics with the Kubernetes platform. And as a demo, we presented the use case for efficient jobs execution. But of course, this is not the only possible use case to be supported within our POC. Other example use cases can be intelligent scaling of deployments and also trend analysis and detection of upcoming out-of-memory errors. Now, a couple of words about the business benefits and costs of this approach. So I would say that there are potentially two main benefits for this solution. The first is that through efficient use of available compute resources, we can somehow limit the total number of worker nodes which are needed in particular time to host the workloads, and this can potentially lead to cost savings, which is something very, very nice, I guess. And another benefit is also a kind of possibility to make the cluster administration a little bit easier. So this can, for example, cover the task like cluster capacity planning, cluster dimensioning, taking care of all kind of safety margins, assigning the right value for requests and limits for resources. Sometimes it may require some measurements to be done. So all this stuff can be automated by using our solution. Well, of course, there's nothing for free, as we all know. There are some costs as well. So Tomek, maybe you would like to take over and discuss this point.
Yeah, it is not so pleasant to talk about the costs and the benefits. But of course, we are introducing some complexity to the system because we are adding a new software components. And also we have to provide the computing resources for them. So those analytics are not easy, so it can be complex. It depends on the methods we are using. But we prepared a simple chart that is representing the model of potential savings and overhead we need to have if we are introducing the similar solution like we presented here. This chart is resources are represented in the number of worker nodes for different cluster size. So the first number here is the nodes, the total number of the worker nodes we are at our disposal, and providing that we have more intelligent scheduler, we can, for instance, increase the overall usage utilization from 30% to 60%. Let's say double it. So in that way, we can use half of our worker nodes to accommodate the, say, existing workloads. So in this situation of the 70 nodes cluster, we could expect that we will have the 35 potential savings. What we have to introduce to devote some of the worker nodes for our analytics and providing some overheads. And the overheads depends on the number of deployments on jobs of the patterns that we have to analyze by our analytical components. But even we are still we could have some potential for savings. Of course, if the lower cluster, then the savings will be lower. But this picture is presenting a general model for where we could see for some savings.
Okay, so corresponding to what has been presented in the chart, we do believe that especially large development environments seem to be good candidates to apply our solution. And we would say there are at least two main reasons for that. The first reason would be that those environments are likely to be oversized a bit. Yeah. And the second reason is that such clusters are likely to have a lot of repeatable workload patterns, both for application-related workloads, which are constantly being deployed in such environments, but also with regards to kind of jobs, different sorts of tasks and things like that. Yeah. So these are the main reasons. Okay, and finally, the takeaways are the following. Kubernetes scheduling framework is open and allows for customization. We made use of it by applying a solution which impacts the scheduling decisions through introducing AI ML methods for resource utilization data. We believe this can lead to potential cost savings, especially for large development clusters, like we said. And it can provide also other benefits as well. So that's all that we have prepared for you today. We are done basically. Now it's time for you to ask questions. So let me check if there are any. Oh, we've got it. The first question. Przemysław Ciesielski is asking, what is the MO in case when lower scoring node is available quicker than highest scoring ones? Is an evaluation done on those unexpectedly free nodes? So I don't expect that there's a situation that some node is available sooner than another one, because we score the nodes. In fact, in the same time, we are taking the pool of available nodes in the cluster, because this is just infrastructure. And then our scheduling is asking a node evaluator, the analytical component we have already presented to you, to provide the scores. So I think this situation would never happen in terms of the process of scheduling that is ongoing within our solution.
Yeah, so maybe the question is also because it may be the impression that we need quite a lot of time to evaluate, to compare the statistics, we could retrieve them, etc.
Maybe it's that sense, okay.
In that sense, it's maybe the question, but our analytical components are producing the fresh models as fast as possible. At least we use such a setting in our POC. But in fact, we didn't investigate it thoroughly if it could be such a hazard. Yeah. So this is.
I would say this is a very specific situation.
Yeah, very specific. But the idea was just to provide some POC when we could learn more and just to increase the precision of the scheduling process in that way.
I hope it answers the question. Another one. How will your schedule behave when a completely unknown pod comes to the cluster?
Yeah, that's a good question.
Very good question.
And quite serious problem, in fact. We are aware of it. So normally, our PC is learning a new pods, and the learning methods, each learning method has some inertia in that way. So it requires some time to acquire the knowledge and the patterns, etc. But we need to decide if we schedule or not. So we haven't implemented it, but we were thinking about two possible approaches. One is to use the standard way, so using the requests and limits that have to be set up. And after that, if we learn the patterns, and we can use the patterns instead of those two values. This is the one point. And the second one is just to, it could be approach when we are deciding to separate one or a set of nodes and scheduling such a new in terms of our analytics spots in the separate nodes, just for learning.
Yeah.
And after that, if we learn, we could just use such a knowledge to instantiate new replicas and new instances. Yeah.
I'm wondering that maybe the idea of the question was also to ask about the default behavior of the scheduler when a completely unknown pod will enter the cluster for scheduling. So if it was the intent, we can say that currently, if there's something completely new for us, like the pod that we completely do not know, do not have any pattern or something, then it will be scheduled under the default scheduling mechanism without introducing any knowledge collected by our intelligent scheduler. And after some time, our intelligent scheduler will be able to gain some knowledge collected from measurements, metrics, etc., like we presented. And then it will be possible to somehow fine-tune the process of scheduling for such kind of pattern that this kind of workload introduce. Another question. How about the communication between a scheduler and your logic? How the communication between a scheduler and your logic was implemented? Well, this is the very simple answer, I guess, because we have implemented a REST API within our analytical components, especially within the node evaluator. So there's an API definition with some endpoints defined for different aspects of scheduling, like some filtering, supported some kind of scoring. So this is something that we have implemented, and just a basic stuff, I would say.
And the scheduler can ask if particular pod can be scheduled on particular node. So 2 parameters, pod ID and worker ID, and the same for the scoring, in fact.
Yeah. Are there any questions? We cannot see anything new. So.
Okay. So I would like to inform you that after this webinar, we will send you a short survey. Please provide us your feedback about this webinar, and such a feedback is usually helpful when we are preparing new webinars. So thank you very much for this.
Yes, for sure. So thank you very much for your attention. See you next time, and bye.
Bye-bye.